there is none, that's sort of magical. And it is, but it turns out, you can actually do this, and it actually works quite well. Yeah, so pooling and striding, upsampling, how do we do it? Well, you can do this in like the most straightforward way you can think of. So there are lots of ways. We'll talk about kind of like the most naive ways, and then more sophisticated ways as we go here. So here's some of the most naive ways to do this. So one is what's called nearest neighbor, and in this case we want to go for something like 2 by 2 and kind of expand the size by 2 in both height and width. We just take all of the new pixels kind of corresponding to what's in each one of these quadrants and just fill them in with whatever was in the original image, right? So, what's that?
Kind of like blowing the vertex.
Yeah, exactly. This is just like blowing it up. It's going to look more pixelated at this resolution, but it's like preserving really faithfully what we had in the input. That is a way of unpooling. There's this other one, which I guess is called bed of nails. I don't know. You don't have to fill everything in. You could just fill in like some specified part of the grid in each of those quadrants. In this case, it's the upper left, but you could choose it to be whatever. That would do it. You'd have a bunch of zeros. I don't know if that's like horrible or not, but it is something. It was some way of going to a larger spatial extent. There are certainly smarter ways. Here is a way that is like the bed of nails, but it preserves some information about what happened during downsampling, that you use that as you upsample. So in the case where you have this really like very symmetric network where each downsampling step has a corresponding upsampling step. In the downsampling, if you say use max pooling, you remember which entry in each of these pools was the max. And then when you unpool, you take that number and you put it into the corresponding spot. This has some like better behavior than like bed of nails and the nearest neighbor, and is totally valid to do. Why might this be better than say like the bed of nails?
I think there's a pixel correspondence. That here we draw the pixel, the maximum pixel from here, and then when we go to the label space, this pixel goes to that pixel. So actually, we want that to correspond, since for segmentation.
Yeah. I mean, it's preserving some information about the original image, basically. So as you go back, it's just like you're not really reconstructing the image here, although you could reconstruct it. These kind of networks are very valid for doing like unsupervised learning, which we haven't really spent time with, but we will later in the course, where you're compressing all this down to like a much smaller spatial extent, but then expanding it back out to its original size, and then just using as your loss function the difference between your original image and what you've reconstructed. So it's similar to that, but of course you're not being supervised by that. You're being supervised by you're trying to predict for each pixel what class is there. But because it's really related to reconstruction, you're doing something like this is preserving some information for the reconstruction by putting these numbers in the max spots. Anyways, it just contains a little more information than some of the other methods, the two other methods that we saw have. Okay, then this is what really is used. These are called transpose convolutions. So transpose convolutions do the opposite of what convolutions do. So where a convolution takes you from some predefined grid size, like 3 by 3 for the filter size, it takes you down to a single point. Transpose convolutions take you from a single point and expand you back out to 3 by 3, but like in a convolutional way. So basically like in a linear algebraic way. So let me just motivate this. So this is what we do with regular convolutions, right? We have our filters. They get, they produce, and here we have some padding as well, and they produce an entry in the output, one entry. And as we slide along, we get different entries. If we have different stripes, then we get smaller spatial extent. But again, this mapping of like 3 by 3 grid to a 1 by 1 grid, to a single entry. Okay. When we do transpose convolution, we're basically doing this in the opposite direction. So for each entry here, this filter that we're going to learn will expand this number out into 9 different numbers. And this is a strike 2 transpose convolution. So strike 2 will take you from 2 by 2 to 4 by 4 in this case. And this entry now gets mapped to another 3 by 3, so there's 9 entries grid. And at any place, like the way that the math works out here, any place where any of these filters overlap, like in these entries here, we just sum the outputs, the red entries and the blue entries. And that's what goes there. Okay, so this has lots of different names. I'm not really sure why, but it really does. Like, you see these names all the time. I think transpose convolution is probably most common by now, but you definitely, so I don't know if you see deconvolution, but you definitely see upconvolution. You sometimes see fractionally strided convolution. That sounds really fancy, but it's just a transpose convolution. Maybe backwards strided convolution. Anyways, these all just refer to the same technique. Yeah, like here's another view of that. Here's the filter that we're learning. Here's the input, and then we're upsampling in this transpose convolution. It's just, again, it's linear algebra, so the entry times the vector. That's what goes here. Then we have that for the blue entry. There's some overlap, so those get added together. And then you can expand this to the 2 by 2 case. Or sorry, not 2 by 2, like the 2-dimensional case. Okay. The reason it's called convolutional or transpose convolution is because you can represent like the convolution operation as this matrix multiplication, and turns out that you can represent what we're doing. By the way, these should be z's. They're x's, but they should be z's. And you can do what you can do the upsampling operation, the transpose operation, literally by transposing this original matrix and matching dimensions, and you get the same output. So that's where the name transpose comes from, and this is why this is probably like the best name for it, because it actually suggests what's going on in the math.
Which one is a filter and which one is image?
The filter are these. So again, these are just 1D examples, and this is the image, but it's the right way to say this. It's been represented in a way that allows you to like write this as a single linear operation, right? This is like moving the filter around. Like writing these in rows is like moving this filter around on the image. Okay, nothing too deep here, and what's awesome is that like you just go to TensorFlow or PyTorch and you just find your transpose convolution layer, and it's all there, taken care of for you. But if you need to do the math, it's not too bad to do, as long as you can kind of keep track of where all the numbers are going. It's just, again, it's just linear algebra, like everything we've been doing. Okay. Yeah. So this was our stride 1 example. This is our stride 2. The stride 2 being the fact that this is shifted over by 2 numbers, or by 2 entries. Same thing for the transpose convolution. So again, this is just a way to learn how to go from smaller spatial extent to larger spatial extent. So once you have that, then you can learn a network like this that allows you to compress the image down to these smaller spatial extents and then extend it back out again and make your predictions per pixel. Questions about that? Yeah.
So basically, the filter that upscales it is a learnable parameter.
Yeah, it's a learnable filter, in fact. I mean,
Learnable filter.
Right, like it's 9 by 9, or sorry, it's 3 by 3, so it's 9 parameters, right? Or it could be 5 by 5. You have it be whatever you want, and it follows. Like there's the same set of rules about like when you stride, like where, like how far it goes.
Mm-hmm.
Just kind of doing everything in the opposite direction. And like the main point to remember here is anytime there's overlap in any of the entries between the 2 filters, or not between 2 filters, but between the same filter just like moved over, then you just add those entries together.
So I've seen like 4K TVs that claim that they'll take a 1080p image and upscale it to 4K.
Yeah.
Would it use like a neural network?
No, it's probably doing something like bicubic interpolation or something like that. That's a more common.
Could you do that? Could you improve the quality of an image?
You could, but that you wouldn't be learning. You wouldn't be learning the operation, right? You would like bicubic interpolation is depending on where on which pixels you're trying to like interpolate between and
if you had
spatial extent.
1080p images and a bunch of 4K images of the same.
Yeah, you could learn.
You can learn how.
Yeah, so like there's a whole area called super resolution in neural networks. That's where you learn to like take downsampled images and properly like make them larger, like super resolve them. And they use, I mean, networks like this, or at least like transpose convolutions will appear, but this is usually like a generative. You're usually learning. This is something we're going to get into after the break. Generative modeling, where you learn to like generate this given the statistics of the input, rather than like learning like the parameters of an interpolation of supply or something like that. Yeah.
Yeah. So in this picture, the model architecture is symmetric. We have the same numbers of reduced layers as opposed to upscale layers. Is it required?
No, it's not required. Nope. Nope. It's pleasing to look at it because it's symmetric, but it's not required. Like that max pooling and unpooling idea. There needs to do that. There needs to be. It doesn't have to be symmetric, but there needs to be. For every downsample, there needs to be like a corresponding upsample of the same side but in the opposite direction, so that it makes sense to memorize the spot where the max number came from.
Should be equal, or the size of
not the layers, just that I guess what I'm saying is like you could imagine it being like you don't need these, for instance. Just the fact that you have at least one transition here to feature maps at the same spatial extent, so that you can use the max pool, use the max pool that you did to do the max unpool. But really, you don't see max pooling and unpooling. You see transpose convolutions because you're actually learning. You're learning to do the upsampling. This is like the whole point of what we're doing here is like end to end. We're learning how to do these operations so that the operation that you learn is determined by the data you trained on.
From low residue to medium residue. So the number
Not
of
residue, just resolution.
Oh, sorry.
Yeah. Resolution.
Low resolution. Okay. So the number of filters from low to medium, is it D2?
Yeah.
Is it
Yeah. So in these pictures here, D2. So this is totally symmetric, right? And everything at this medium resolution is using the same number filters, but it doesn't have to be that way. You could do it any way you want. That's like what's good and bad about neural networks. Infinite possibilities, but no way to choose the best one other than try them all. Okay. Other questions? Yeah.
Do you have to increase the number of filters as you reduce the?
No, but that's one of the reasons why you want to reduce is to allow you to have more filters, because each one of those corresponds to a feature.
Don't you lose them once you upscale again?
Yep, but that's okay, because think of this as like having encoded the image in some way, like you compressed it, you've encoded it, and all this part of the network's there for is to like decompress it. So it's like you learn an encoder and a decoder, or a compressor and a decompressor. Yeah, when we do generative modeling, we're gonna see lots of ideas like this, encoding and decoding. Yeah. Okay. Cool. So that's that. Semantic segmentation. As long as you have graduate students who can label all your images, then now you know how to model it. Okay. So now how do you do these? Locate all the objects in your image and classify what's in it. It's actually pretty tricky, but these are very cool models and very popular. You probably have seen lots of examples of these, as you read about neural networks and such, where they, you maybe see a video, or the video as it's, as the frames are progressing, there's a bounding box around the object, and it has a label usually in it, like what class this is, and then usually some kind of like confidence. It's usually just like the probability or likelihood of that for the class for that image. But anyways, these are really neat models. So how does this work? Okay, well, you basically have two things you need to do here. You have one, you need to draw the box, and then two, you need to classify what's in the box. So to draw the box, and this is maybe, you might be wondering, like, why a box? Well, a box has like 4 coordinates. So there's like 4 parameters associated with the box. You only have to learn 4 parameters. If you had something with more size to it, some, like polyline or something like that, like there'd be a lot more parameters. But if you draw a box, get something nice and rectangular, you only have to learn 4 coordinates. So what's done here, like essentially, and we're going to see all the ways that this is done, is you need to learn like some parameters that describe the box. So usually there's something like a corner, like an upper left-hand corner, and then a width and a height, and that's the box. So this is now a regression problem. So instead of just trying to just classify what's in the image, you're now doing regression where you're trying to predict like the continuous, some continuous variables. So they're obviously not totally continuous because these are images, and so that's quantized. But anyway, so you're trying to find some coordinates for the corner and how wide and how tall. So you're kind of like doing both of those together. That's going to be like the kind of the core idea as we go through the variety of models here. Yeah.
Yeah. So in this setting, say the training and the testing data set should be of equal size because we are trying to predict the coordinates. Right. So the image.
Well, each image might have a whole bunch of different objects in it, and therefore boxes in it, right? So we might need to predict many boxes.
Right. I mean the size of the whole image should be of the same size because the coordinates is dependent on the size of the image.
Right. I see what you're saying. Yeah. But you can usually think of these like x and y as like offset from some corner of the image.
Proportionally?
No, just like number of pixels. Okay. Right, and then W and H are also number of pixels. So again, like it really is, because it's quantized, because it's a pixel, like it really isn't like truly regression, but we treat it as a regression problem because you don't want to have 300 and something classes for your width and 300 and something classes for your height or something like that. So anyways, this is like the basic idea. We need to be able to predict the coordinates of the box. Right, so we know, softmax for softmax and cross entry for the classification problem, and something like an L2 loss, or it could be an L1 loss, but something that allows you just to compare coordinates to each other and compute the difference between them. So some sort of, like vector distance for the loss. And like what we'll see, like a lot of how these are done, although there's lots of variation here, but a lot of how this is done is you, like in this basic one, so if you took ImageNet for the classification problem where there's just one object in there, you can get away with doing something like this, which is from your final fully connected layer, you could have two heads to this network. So one for the classification, one for the regression. You get two losses, one for each, and you want to add those together, usually with some weight to kind of express how important one task is to the other, and for one combined loss that you'll optimize all at once. And this is like the really nice thing about neural networks is that this is how this typically goes. Like, it doesn't matter how many things you're trying to do with it. You can just keep adding loss terms to this, balancing it with the rest of the loss terms in there, and optimize one problem altogether, and hope for the best. Keep trying to find the best thing.
Is this for just a single object? Right?
Yeah, this was just a single object. Like, this is kind of just the base way to talk about it. We're gonna go much further than this real soon. Yeah, so if this is all you're doing, or even if you're doing like you're working with problems where you're trying to do more than one object in an image, it's not uncommon to start with networks that are pre-trained, like on the ImageNet classification problem. That way, like you're starting with a network that already has filters that are really good at like detecting the kinds of things you care about in images. And then we'll either fix those and have some other parts of the network that will learn, or will allow the whole network to kind of be fine-tuned. It just depends on how you approach the problem. But this is really common here is to start with pre-trained models and then push beyond that. Okay, so I think you were kind of getting at this earlier. How does this work if you have lots of objects in an image? So if you have just one, the way that it's just set up is really straightforward. You're going to have 4 coordinates you need to predict for the bounding box. You have an object in there. You can do them both together. But usually you won't know, or there can be a variable number of objects within an image. You want a method that will allow you to deal with variable number of objects in the image, right? So that's a piece of what we're trying to do here. Like, look at all those little diagrams. You want to be able to draw a little bounding box around each one of those. I don't even know how many there are there. Take a while to count. Okay, so how does that happen? All right, so like we did in the previous one, kind of build up from simple ideas and get to more complicated ones. So again, you could start this by sliding some window of some size around your image, and then every time for whatever the size is, you can try this for different sizes. Whatever you have here, you can just say, okay, like take your pre-trained network, like reshape what's in here so it fits into the network, and then do the classification problem. Is there a dog in here? Is there a cat? This has like an empty class like the background. Yes, you say, okay, great. And I slide over by a pixel or a couple of pixels, and I do it again, and I do it again, and I do it again. Like that. So this time I slide it over here, and it's like, hey, look, there's actually a dog in there. But there's no cat in there, and there's no background. Great. And so forth. What's the problem with this?
Many windows.
That's right. So this feels pretty hopeless at first. There's if you sort of start this from like a kind of a constructive way of doing it, like I'm going to try all the bounding boxes in all the positions that could go into the image, this is going to be really, really, really slow. So that's not how we're going to solve this problem. So one of the first attempts at this was to do what's called region proposal, or selective search. So they're going to be SS throughout some of these slides, and this SS refers to selective search, or this idea of region proposal. So the original way this was done was to do some pre-processing on each of the images before you did training. And the idea was, to use some like very simple, like computationally efficient methods for like finding what's in quotes here, blobby regions. This is just like regions that have like very consistent like coloring or textures or something like that. And those will be our, those will be the regions that we actually check for containing objects. Obviously, we're not trying all the bounding boxes in all the positions here, but this is like a pretty good way to start. And like the original papers on this would create about 2,000 of these region proposals, or these regions, proposed regions for every single image, and that was fairly computationally inexpensive. Saying like a few seconds on the CPU, so you parallelize this across lots of cores, and you can run this overnight, and then you come back in the morning, and now you have regions. It takes up a lot of disk space, obviously, but whatever, there it works. So, how do you use this? So, the first model for this is this RCNN, and in the original paper here, for some reason they use this image and said that this image is always associated with all of these region proposal methods. So that cowboy is famous. So anyway, the R here is for region, and so RCNN. So what happens in RCNN? Well, you got a bunch of things that happen here. So the first thing is you create these region proposals. So they're called regions of interest, ROI, not return on investment, but regions of interest. So you start with those, and in this way of doing it, you have about 2,000 per image. And what you do is each of those you rescale the image so that they're all of the same size, because we're going to put these all into the same convolutional network. So we need these all. So the convolutional networks take images of the same size. So we have to reshape them all. And then once we've done that, we then pass them through our convolutional network. And we can learn this from scratch, or we can start from pre-trained network. It's usually starting from pre-trained network.
Different networks with different
No,
weights.
all the same network. All the same network. So each one of these is the same network. Shared, all have the same weights. Then, for some reason, I really have no idea why this was done, but there was you did that first. I have some more points on here in a second, but you did that first, and then, in the second step, you took the features that came out of that and did this. You trained this SVM on those features to say to classify what was in that region. And then you had another head. Well, so this is going to be done in 2 stages. So then you have, from those same features, you also predict what the actual bounding box should be corresponding to that. So you know what it is, what region it is. So now you predict it, and that was it. So it's really strange. I don't really know. I don't have a good understanding of why they didn't do this all just end to end from the beginning. That's what's coming next. You know it's coming here. If you have learned anything so far, we do everything, try to do everything end to end. But yeah, it just has this kind of weird way of doing it. So you start with a pre-trained network. You fine tune it doing classification. So this is softmax with cross entropy. And then once you fine tune that, then you just forward everything, all the regions through the network, get some features, and then train these SVMs to do the classification and then to do the regression for the bounding box. And did it in 2 stages. I don't know why, but that's it. As you can imagine, this is actually really slow. It took a lot of this space because you got all these regions that you're keeping track of. And yeah, so there was kind of an improvement on this that sort of sped up this inference stage called SPPNet. I'm not going to spend a lot of time learning about it, but it sort of sped this up, so it wasn't 47 seconds per image. All this kind of forwarding through all these different pieces of that, or regions through different parts of the network. But didn't change like the fact that this is like trained in these multiple stages. So that's RCNN. Then you got fast RCNN. So what are some ideas for how this could be made faster?
Animation action.
Okay.
Reduce the proposals.
Okay, reduce the number of proposals. All right. Yeah. So like, if you're researching on this, you're like, okay, this kind of works, but it seems kind of goofy. How do we speed this up? Well, here is a successful way, and this is what we're talking about today. Fast RCNN. So what it did is to take a pre-trained network and forward the image through it to like the COM5 layer. So actually they use a VGG19. So you have the well understood COM5 layer there. They forwarded this image through the network up to that layer. And so now what you have is you have this like spatially reduced version of the image with a whole bunch more channels. So we start with that, and then we do region proposal on that. So not on the original image, but we do region proposal on the feature maps coming out of the COM5 layer. So already this is a lot smaller and possibly better features for detecting objects in the image. And then they did this really interesting trick called ROI pooling, which I got some slides here to say what it is. But this is where like a huge kind of speed of benefit comes in. And I think it's next, yeah. So ROI pooling, so region of interest pooling. So the way this works is like once you have a region, a proposed region, you actually have this at the COM5 layer. So this is kind of showing it map out to here, but so it's not exactly around the whole cat. Anyways, so you've got 512 channels at this COM5 layer, and the region. So the spatial extent here. I don't know why I showed 15. It should be something else, but you have the original set of features, and then like your region now is going to be the region of interest is going to be some subset of that. So again, that changes per proposal. So the idea is now within that region, divide this into a grid. This is showing 5 by 5, but it's actually 7 by 7 in the paper. Divide this into a spatially extended grid of 7 by 7, and do max pooling in there. So like so you have this feature map, which is already an abstraction of the original image. It's of some extended size, in this example, 18 by 8. You then like draw, this kind of imaginary grid of 7 by 7, and so in the 49 cells that you have there, entries that you have there, you just do a max pooling. So like, it might be this bunch here, whatever is the largest value goes there. So now you've worked your way down to this much smaller spatially extended region of 7 by 7. And then from there, you do a couple of fully connected layers, and do the predictions, the classification and the bounding box from those. So this is a method for what was originally like working with, like very high resolution, like very large spatially extended regions of interest, to actually, in a very quick way, getting to very, very manageable sized regions to work with and for making the predictions. So this is called ROI pooling. It's probably like it should feel kind of weird. It's like really coarsening the image, but it actually worked quite well. So the idea is you forward through here, you get these regions of proposal on the COM5 feature map, you do the ROI pooling, so now everything is of, in this case, 512 by 7 by 7. then you have your fully connected layers that are again like the same fully connected layers from each one of these regions. Think of these as, each one of these is like a sample that you're training with. And then from there, you do your predictions for both the classification, the softmax piece of that, and for the regression, the bounding box part of that. So now this is actually learned all end to end, yeah.
So right there at that softmax classification, you're giving a softmax classification to each ROI, is that correct? Or you're
yeah. So like, I know there's a lot of arrows here, but just really, there's, for each one of these regions of interest, there's one contribution to the loss, right? So like, so like the full thing will be a bunch of losses all add together for each one of these regions of interest, or like average together, for the batch. So it's the same network, right? Like use this. This is all the same network. This is the same fully connected layers that's connected to each one of these, and then from there, the same softmax weights are learned, and then the same regression is done. But you're doing one of those for every single region of interest, and those are all being averaged together with loss. So now you're learning this end to end. Yeah, question.
That's a basic question. How do they find out the proposal area?
They use exactly the same method as was used in for like the original images that we talked about. The same selective search, but now just on the confined maps, feature maps. So yeah, that should seem weird because like, what does a confined map have? But that's what they do.
So are the size of ROI layer of the same?
Yep. So like that's like, one of the points of this is the fact that like when you come out of the ROI pooling, everything's of the same size, even though the regions of interest were of different original sizes. When you do this like portioning by drawing a 7x7 grid and then doing the max pooling, it's forcing where what you had here to the same 7x7, and then by 512 channels.
So would this fully connected layer be like 512 times 7 times 7? Like
no, because fully connected layers are vectors, right? So this is 512 by 7 by 7. So you'd multiply all those together, right? So you turn that into a vector. So now you have something of size 512 times 7 times 7. That's what you meant. Okay, yeah, right, exactly. And then you'd have a couple of different fully connected layers to like really reduce the size of that. Go from whatever that is, 512 times 7 times 7 to something much smaller. If this is ImageNet, then I need to go to this fully connected layer needs to have to be of size 1,000. So I can apply softmax to do the cross entropy loss for that. And then you would use that same fully connected layer to also predict the bounding blocks. So like that fully connected layer is doing double duty there. Which is cool. Like this is one of the really cool things about neural networks is that like you're like asking the network to learn to do these things, like whatever are the things to be done. And with a little bit of skill and experience, you can get it to do these things. And so now, not only are these features good for classification, they're also good for the bounding box problem. So like it's kind of it's changed what information is actually in that final fully connected layer. Okay, so this now can be learned end to end. Linear plus softmax means that we go to linear. That gives us a score, and then we apply the softmax and the layers for the bounding blocks. And we add those together. So yeah, it's all learned end to end. That's just showing you like cool arrows for backpropagation. Yeah, really great. Is this really fast? Well, yeah, this really sped things up in terms of training time. About a tenth of the time to train a fast RCNN, then an RCNN, and then test time, the inference time, is much, much, much faster. But you can see, if you're like really, optimization crazy, you can see that like, so the blue and the red, the difference between them is so inference time, including the region proposals and excluding the region proposals. So you can see that like the inference time here is dominated by still doing the region proposals. So if you like have a need for speed, you might think, okay, how do I make this faster? Somehow we got to get rid of the region proposal. We got to somehow make that faster. So now we have faster RCNN, and it's basically what we had before, except that we actually learn to propose regions. So, so what you have is a network for producing all of these coordinates. It's actually trained. It has its own set of heads, and it's trained with exactly the same losses. So there's also classification loss for what's in the proposed region, and also a regression. So regression loss for proposing the bounding boxes, and then whatever's produced by that network is then used to propose the regions of interest, and then you do the pooling, and the rest of the network's the same as before, fast RCNN. So this is actually now bringing the ROI proposal in to be learned. So now this is like totally end to end. You don't have this separate step that you would need to do beforehand, this pre-processing and proposing like 2,000 regions of interest. Here we're going to learn to produce 2,000 regions of interest.
So it takes examples from the ROI finder.
Yep. Yeah. So we train something.
And then it just finds.
Okay. Exactly. Yep. Wherever you have labels, you use them to train this thing end to end. So it turns out, like, if you can just do this as part of the network, then yeah, you don't have to generate all these regions. So you can. This is actually much faster. More questions about this? Yeah. So now faster RCNN inference time is again like a tenth. So over a period of about 4 years, you go, or 3 years, I think it is, you go from just the ability to do this at all to like very, very, very fast end-to-end networks. So really cool. Like this is a good example of like the kinds of progress and how it's made in neural network research.
How about training time?
I don't have a slide on that. Sorry. Fast. No, it's actually probably slow. Because now you have a lot more to train. I don't know. I never trained one. Okay. All right. So there's some variants on this. So there's something called mask RCNN. So this is basically a faster RCNN, but instead, what you do is in each of the regions of interest, you actually want to learn a binary mask that is like, meaning like you're assigning a 0 or a 1 to all the pixels within that region, a 1 where the class is, where the instance of the object is, and a 0 where it's not. So you have this additional, so it's just faster RCNN, but you have this additional step which does the classification. So it's interesting, it actually learns like one mask per class, and then you use that mask for whatever is like the predicted class. So it actually adds quite a burden to the network, but it allows you to do this like the segmentation of the object within the bounding box. And it has this additional step called ROI align, and it's like ROI pooling, but so when you do the pooling, you like go to this kind of course 7x7, and you use max pooling. So ROI align is very similar. You can see there's like a 14x14 here, so it's a little bit larger to be able to learn this mask better, but it also does like a much smarter like interpolation of what value should go into this kind of pooling operation rather than just max. It's got a like a, I can't remember what it is now, but something like a bicubic spline to like decide what value should go in there. So it's like trying to preserve the information as faithfully as possible in this downsampling step. But anyways, the point is that you produce these masks, and so now now what you can do is, so you get your regions of interest, and now you can say, like, within that region of interest, what is like which pixels correspond to the object that we classify with. So it's very cool, and it like works really, really well. And this is from the same people who gave us ResNet and all those good things. So they were busy for a couple of years. Yeah. So like this is awesome. This is like really state of the art kind of stuff for convolutional neural networks. Yeah, you can teach it to do pose estimations as well, as long as you've got the labels. Okay, so can we do even better? Can we make this even faster? So the answer is yes. And so there's a network that came out kind of around the same time called YOLO, which is you only look once, not live once. And what it does is it does this kind of portioning of your image, so divide it up again to like, you know, 7x7 grid, and then for each cell in the grid, you have this like predetermined set of bounding boxes that you're going to try. And there's usually just a couple. You know, there's like, you know, rectangles of different aspects, but only just a few. And what you do is you start with those bounding boxes as something like a proposal for like, hey, there might be an object in here, and then you learn to adjust the bounding box to actually fit the object better. So what you do is you learn how you ought to, starting with that bounding box, how you ought to change each of the coordinates of that bounding box to put an image in there, or to put an object in there, and you have some sort of like column. This is usually like the probability associated with that object, with that class of being in there. And so this allows you to, like, in a much faster way, learn to create these bounding boxes. So it's very similar in spirit to what we've been looking at, but just, you know, kind of a different way of approaching it. I like this a lot because it's like, it kind of makes sense. It's like you start with proposed regions and then kind of reshape them. Like when you know that with some confidence that you've got an object in there, let's like now reshape that to fit around the image, fit around the object in that. Okay. Yep. One big convolutional network. Okay. So yeah. So there's this great review paper of kind of all the things we talked about today. If you want to look at that, and you can read about all these and learn about all these all at once. Anyways, there's lots of kind of ways of doing this. You know, what we didn't talk really anything about is how these. So I did mention that there's like a VGG network to get you to like the Conv5 layer, but you could do this with any convolutional network pre-trained, or you could learn it, and you could so like that initial network, like starting with the fast R CNN, that was used to forward the images through to get you a feature map. That could be a whole bunch of, that could be from any one of the many convolutional networks that we've learned about. You know, like what exactly the task is that you're doing will depend on, or like what you choose, how you choose to use that backbone will depend on the task you're doing. And takeaways are that like fast RCNN is slow but more accurate. SSD, which is like just a slight variation on YOLO, it's much faster, but it's not as accurate. Anyways, this paper is a great paper to kind of read about this, and these are really fun kinds of models. Yeah, so how has using these convolutional networks, these deep convolutional networks, impacted the task of object detection. So this is kind of similar to what we saw for the ImageNet classification task. This is so the average mean precision of the being able to correctly predict the object in the each object in the image, average that over the objects. You can see how so this, there was progress being made, but then all of a sudden we started using convolutional networks, and we started to see huge improvement. This is a particular data set from Pascal. Anyways, deep convolutional networks to the rescue. And what's really cool too is that, like, it's probably a little bit out of date now, but there's, because like this is like a really common task that people want to do, there's really nice frameworks for actually working with these, like with pre-trained networks. So like if you just want to kind of set one of these up and like have the camera on your laptop, like start drawing bounding boxes around what it's looking at and classifying what's in there, you can just go grab these pre-trained APIs and plug them into some basic script for processing your image or processing the frames in your coming through the camera, and all of a sudden you now have this cool party trick you can try it on your friends, show them how smart you are. Yeah, that's it. So we're out a little bit early today. Happy to answer any questions or want to come and ask me.
So, yeah, this one's curious, like, I want to make sure I understand this. So, when we initially set up our convolution, so I think
No, three choices. Here is it's corresponding to the alpha. So 5 by 5 is the spatial. 3 is the number of 6 is the number of
and this is 3.
Yeah, so it's not just 3 connections, you have 3.
So your alpha will 6 channels.
Yep, 3 by 3. And this is also why you have the bias being of size 6. Yeah, and here's, kind of back to this. Now, like you were saying, 3 by 3. The input number chose 6, and that's actually happened in the previous one, right? Now you're 9.
And now the whole connected layer. And so I can't tell, is it it's like the height and the width of the layers?
Yes. Well,
multiplied by 9 channels?
Yeah, right. So like, what's the size of the feature map of this one? Because you've been doing pattern, you preserve the spatial extent, which is 32 by 32. Right. So you have, so in that feature map you have 2 by 32 dimensions. You have that many entries, and flattening that out into vector that size. And the output again is 10. Right? And you're trying to have 10 processes like that.
Okay, I think that was, I forgot that you were preserving the spatial, so not
yeah. I mean, you don't have to. That's a choice you can make.
But when we get down to this, like we have, then it would just be whatever.
Yep.
Cool. Alright, great, thank you.
Yep. Who's next?
Alright. So,
It was.
okay. One of the weird things that even when I tried to test it, so when I trigger reshape, it only have that shape.
This one, there's a lot less information here than there is here. There's a lot more information here than there is here. So this is going to do a higher whatever it is you're trying to do.
And then
Yeah.
maybe that's what my thing was
Yeah, so like the way that point here is actually executing it. So fully connected zero. No, you need the full fully connected because that's what converts into the number of classes.
You can't do it on your own. You gotta do it. You have to figure that out. Yeah, you gotta do it from the part of the final project is actually.
Oh, nice.
So convincing. Be convincing. I'm sure it'll be interesting. Be convincing.
I didn't expect it to be.
There's a lot of things. There's like 50.
During class last time.
There's gotta be one. You'll get it.
Yeah, I feel like I was actually just about to class for that whole everything.
I mean, you could resubmit it.
Nice.
Write me an email or maybe just write a direct message to Canvas. I'll sign over.
Should took another detail.
And that you talk about this,
But
they know.
the I existing understand so much better.
And I was like,
Yeah. I know YouTube is like my second education.
Okay, so now what I'm
yeah, it's doing kind of like what it says here. So what you might want to first it segments cells. So, and then so now you have this statistics per cell.
Same. So you know how
whatever you want.
TensorFlow
Just doing some cell analysis creator if you want to create finals and
it was like type.
No, that work. It's Java, so basically the same thing. Feature like this. Think of like the last layer of the software.
So yeah,
think of that as
so
being like
right.
feature of like cell profiling features.
So
Vector cell profiling features.
if you're gonna same just means you're using this model, but you can change it.
But you don't know
use
how to create it. It's kind of like you create like a black box. You don't know what the function is, and like what that exactly is, but you can kind of learn to do that using some of the techniques we learned last time.
So if you want to do if you want to insert the
So it's
pattern,
it's the difference between like learned features and
a list.
design features.
Where this is the padding for this.
Yeah, they're all basic features.
This is the padding for this.
So what are you working with?
so in this one, we only want pattern.
That's correct. So you want the padding to be 2.
Okay.
If you want to watch the cool type in phone sounds.
And I'm pretty sure that's
Yeah.
for the
Yeah, so that's
I hope so.
all that research.
And so what's solid profiler
Find out.
used for? Like what kind of assay are you guys doing?
Yeah, so we take neurons from ganglion and we dissociate them, and then we put a bunch of different pharmacological compounds while we create and so we get 7,000 traces, and we get, sorry, 7,000 cells, we get 7,000 traces, which is like,
So track this out if you do that cell over different.
yeah, so the way we kind of break it down is we take a starting image, we cell level. So we make an
Would that
ROI.
change for all of
其
your?
实它的是每一年那你说那多少钱？
So what's something?
So self-profiling is finding areas of interest. We have 7,000 cells, we know they're all different, so self-profiler draws the circles around.
Yeah.
And then we have like 5 additional markers. And self-profiler gives us all of the statistics for each cell on all those things. But
But like over time, like you do it per frame or something like that?
yeah, so then we
So you watch those change?
Yeah, yes, we watch. Well,
Yeah,
this
just
is
one
one
of
will
those.
change. Yeah, this is
One cell?
one or channel, so just watch the calcium.
Got it.
I
I see, so you're tagging calcium.
比如说我们现在这个发现方法，
You know, plus or something like that, and you're imaging
每
that.
一个方法
Oh, I see. So it's all
都可以跟它做一个视频，一个网络，
What are the element? Yeah, we
So-
got traces.
两个
Well, this is just kind of height on
一个方
top
法
on
自己的，
We
Top
I filled up the
可以
huge
大家知道，也不是方法，
left,
可
right.
以习惯的去做这些，
So-
往下往下面做。
So
we apply something
是的，很多的。
like this, and there's
比如说第一季，
tons of cells here. On this cell,
由第一个来
apply
这个
this compound.
Well, padding means that you're going to do it left and right.
Apply
因
compound.
为这里要
Go
有
to zeros on the left and
cell.
the right involved.
这个注意点跟我以前学的有点
Okay, that's
像
what, but it's
Okay.
so we're going to zero evolving along this
然后去把那个
rather than having for saying some heading on this side and some heading on this side.